Hi, welcome back to Calculus. Today in section 9.8, we're going to be looking at Taylor and MacLaurin series. So these are generally pretty nice, and they do some interesting things. So let's take a look. So let's start with a big definition. This whole board is one big definition, and I'm even going to have to move my computer to show it to you. Let f be a function with derivatives of all orders on an interval containing a as an interior point. So basically, we have a function, and somewhere near a, you have all the derivatives you could possibly want. The Taylor series generated by the function f at x equals a is this wonderful sum. The sum from k equals 0 to infinity of the kth derivative of f of a all over k factorial times x minus a to the k. So what? Let's try that again. It's this guy. It's just f of a plus f prime of a times x minus a times f double prime of a over 2 factorial. Notice 1 factorial is just 1, so that's why there's no factorial down here. 0 factorial is just 1, so again, that's why there's no factorials on these first two. Times x minus a squared, all the way out to the nth derivative of a divided by n factorial times x minus a to the n, and then on forever. Continuing, the MacLaurin series is just a special case of the Taylor series. The MacLaurin series is just the Taylor series generated by f at x equals 0, which kind of makes things nice. Instead of all those a's, we have actual numbers here, 0. A will be a number if you're trying to do a Taylor series, so that's not to worry about, but 0 is always nice. So it's sum k equals 0 to infinity of the kth derivative of f at 0 divided by k factorial times x to the k, because again, a is 0, so we just have x, not x minus a. So it's f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial, x squared, and onward. So let's get some more stuff on the board. Let's actually find a Taylor series. That sounds fun. All right, so let's look at this example. I want to find the Taylor series generated by my function f at a equals 1. So you can see over there I have a function. F of x is equal to 2x cubed plus x squared plus 3x minus 8. Now this one is super nice because it has, you can do derivatives forever, but they all turn into 0 eventually. So you can see I took the derivatives, and by the time I get to the fourth one, I get 0. So for any derivative where n is greater than or equal to 0, n is greater than or equal to 4, we get 0. So what I did is, since I had the derivatives, I could plug in 1 into all those derivatives, and I did. I got -2 for f of 1, 11 for f prime of 1, 14 for f prime of 1, and 12 for the third derivative of 1. After that, they're all 0. So I can put this together as a Taylor series. So the Taylor series is just f of 1, so there's my -2, plus f prime of 1 times x minus 1, there's my 11, plus f double prime of 1 over 2 factorial, so that's 14, divided by 2 factorial, you get 7 times x minus 1 squared, and plus f triple prime, 12 over 3 factorial, that gives me 2 times x minus 1 cubed, and after that, everything else is 0. So this is a very simplistic example because it was a polynomial, and eventually everything turned into 0, but there we go. That's our Taylor series for this. So let's look at some more on the next board. All right, finally, let's look at Taylor polynomials. So a definition, let f be a function with derivative of order k, where k goes from 1 up to some number, capital N. Then for any integer n between 0 and capital N, the Taylor polynomial of order n generated by f at x equals a is. All right, so the nth Taylor polynomial, it's just the Taylor series cut off at the nth term. So we have f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial, x minus a squared, all the way out to the nth derivative of f of a over n factorial times x minus a to the n. So let's do this fun little Taylor series. Find the Taylor series and Taylor polynomial for f of x equal to e to the x at x equals 1. So this is really pretty cool because at x equals 1, we're really just finding e. So we're going to have a series here that generates e for us, basically, more or less. All right, so importantly, since the function is e to the x, all of its derivatives are also e to the x, which means when I would need to plug in 1, f of 1 is e, and all of its derivatives, when you plug in 1, are also e. Very, very, very nice. So let's slide this down so you can see the rest of the board. There you go. And let's see. The Taylor series is just f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 over 2 factorial times x minus 1, which I should have a square on it. All the way out to f, nth derivative of f of 1 all over n factorial x minus a to the n. But the good news is all of those f values are just e. So I get e plus e times x minus 1 plus e over 2, because 2 factorial is 2, times x minus 1 squared. And it all ends up adding up to the sum k equals 0 to infinity of e times x minus 1 to the k all over k factorial. And then the polynomial would be, for the Taylor polynomial of nth order would be p sub n of x is equal to e plus e times x minus 1. It's basically this thing all over again, but now it's cut off. It doesn't go out forever. So all the way out to e over n factorial times x minus 1 to the n. And there we go. Taylor series, Taylor polynomial. So have a wonderful day, and yeah, good luck.